Good morning, students. Let us discuss today Gauss divergence theorem. This is very important theorem as far as this vector calculus is concerned. The Gauss divergence theorem, also known as Gauss theorem. Sometimes it is called as divergence theorem. So either it can be called as divergence theorem or Gauss theorem. And this Gauss divergence theorem relates the flux of a vector field. So this is the flux of the vector field. So definition for the flux of a vector field outward. Flux of a vector field through a closed surface S to the divergence of the field. So this is the divergence of the field within the enclosed volume. So this is dive A, and this is your flux. So surface integral to volume integral. So we can convert surface integral to volume integral, and this is your outward flux, and this is your divergence of the field. And Gauss divergence theorem, which connects surface area into volume integral. Simply, it states that the surface integral of a vector field over a closed surface is equal to the volume integral of the divergence of the field over the volume enclosed by the surface. So this is the formula for Gauss divergence theorem. This is double integral and this is triple integral. Double integral A dot ds, which is equal to triple integral div A dv. So which connects surface integral into volume integral. Okay. So this is your outward flux of a vector field, and this is your divergence of the field. Outward flux of the vector field is defined as, it's a measure of how much of the field passes through the surface. So flux is nothing but which is coming outside, or which can go inside also. Divergence of the field is measurement of the tendency of the field to flow outward from the point. The physical interpretation. A divergence theorem provides a powerful connection between the behavior of a vector field on the surface and its behavior within the enclosed volume. Sources and sinks. What are the applications? We will find out what are the applications. So before that, we should know what are the sources, what are the sinks. If the divergence of the vector field is positive at a point, it indicates a source. So the flux which is coming out from one point, we call this as positive point. Suppose the flux which is going inside, we call this as negative one. That one is source, another one is sink. Source is, if the divergence of the vector field is positive at the point, it indicates a source. That means which is coming out, where the field originates. And if the divergence is negative, it indicates a sink. It means a point where the field converges, it goes inside. What are the applications? It can be applied in fluid flow. In fluid dynamics, the theorem can be used to relate the flow of a fluid through a closed surface to the rate of change of fluid's density within the enclosed volume. So it is used in the fluid flow. It is also used in electromagnetic fields. The theorem is also fundamental in understanding electromagnetic fields, helping to relate the electric flux through a closed surface to the enclosed charge. So now we will look into the detailed explanation of Gauss divergence theorem. As I said earlier, this can be also used as Gauss theorem or divergence theorem. The definition for Gauss divergence theorem is, Gauss divergence theorem says that the surface integral can be converted into volume integral. Surface integral can be converted into volume integral of a closed surface and vice versa. Volume integral can be converted into surface integral. Surface integral can be also converted into volume integral. Now you just consider the surface. Consider a surface. We are going to take a small volume V, and A is the vector field, and ds is perpendicular to the small surface which we have taken. Okay. So where ds is here, A is a vector field, and the angle between these two is nothing but theta. The flux of a vector field A over a closed surface S is equal to the volume integral of the divergence of the vector field over the volume enclosed by the surface S. Let A be any point on the surface vector field, and ds is the unit outward normal to A as shown in the figure. Let us consider a finite volume V of any shape enclosed by the surface S in the region of any vector function A, then the flux diverging from the surface S of volume E is given by this. The flux which is coming out from this small surface area is nothing but phi equal to A dot ds. We know already this formula. The definition for flux is nothing but A dot ds. Okay, A dot ds. Now we have divided into small volume. See, this is bigger surface. We have taken the small volume. Similarly, we can have another volume V1. We can have another volume V2, V3, V4. So lot of volumes we can have on the surface. So now dividing the volume V into large number of volume V1, V2, V3 dot 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 Vn enclosed by the surfaces S1, S2 dot 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 Sn respectively. Then the total flux over the surface S phi is given by phi equals A dot ds. This is total one, which is equivalent to A dot ds1 for the first surface, for the second surface, for the third surface. Is it okay? See, here we have taken only a single volume. Similarly, we can have more volumes V1, V2, V3, V4, and we can calculate the total flux, which is nothing but the summation of all the individual flux. Okay, they are all flux, individual flux. So instead of this, I have written instead of this you can write summation. So I have written as summation. So we have written summation. So phi equals I equals 1 to n double integral surface Si A dot dsi. Okay. So this can be written as a summation. Now I am going to multiply and divide by Vi, total Vi. I am going to multiply and divide by Vi. So now I am going to multiply and divide by Vi, that will give me this. See here in this expression, I am going to multiply, this is total, okay, total flux. I am going to multiply this by VA and VI. I am going to multiply and divide by VI. That's all. Multiply and divide by VI. Now, if n is sufficiently large, then the volume VI becomes infinitely small. Suppose if n number of volumes enclosed are very, very large, then Vi becomes infinitely small. So if Ni tends to infinity, that means Vi tends to be 0. In that limit, this is equivalent to di Va. So definition for di Va is nothing but this, A dot ds per Va when limit Va tends to 0. So this is the original definition for your di Va. Okay, di Va, del dot A. So del dot A is nothing but this definition. Okay, when provided Va tends to 0, Va tends to be very, very small. So now instead of this we can write di Va. So Vi di Va, and I am going to replace summation over integration, and this Vi becomes dV. So we have now dV integration dV, this becomes di Va, which is nothing but your del dot A dV. Left hand side is nothing but A dot ds. So A dot ds equal to triple integral, because the volume consists of x, y, z. So that's why we have removed the summation and we have inserted triple integrals x, y, z. So this represents volume. So triple integral del dot A, and this summation over Va is replaced by dV. Okay, dV. So left hand side is the flux, right hand side is nothing but your divergence of the field, vector field, which is nothing but your Gauss divergence theorem. So this equation is a very, very important equation. We can convert surface integral into volume integral. Similarly, volume integral into surface integral using this formula. Okay. So this equation is called as Gauss divergence theorem. Now let us solve some problems using Gauss divergence theorem. If R is a position vector of any point on the surface S enclosing a volume V, find R dot ds. So we are going to find out R dot ds. We know that Gauss divergence theorem is given by this. The expression for position vector is given also, we know already. R vector equals xi plus yj plus zk vector, we know already this. So now substitute here r dot ds. R dot ds is nothing but your r dot ds is nothing but instead of r you can write this. Instead of ds you can write this, correct? So no, r dot ds is nothing but div or dv. Okay, div or dv. Okay, div or dv. What is the expression for your div? Del phi equals I d by d phi plus j d by dy plus k d by dz. So instead of this you can write, so instead of div r you can write this, correct? Your r is here and your dv is here, so dv is missing here. Okay, dv is missing here, so you have to write dv here. Is it okay? This is your div r, this is r, this is dv, dv is missing here. Now as usual a dot b, that will give you dx by dx, correct? Dx by dx, dy by dy, dz by dz. So 1 plus 1 plus 1, 3, triple integral dv, that will give you 3. So this is the answer, 3v is the answer for this problem. Find r dot ds, r dot is nothing but 3. Okay, so using Gauss divergence theorem we have found out. Now we will go for the next problem. Using Gauss divergence theorem, evaluate double integral over s x cube dy dz plus y cube dz dx plus z cube dx dy, where s is the surface of the sphere, x square plus y square plus z square equals a square. Now we have to use Gauss divergence theorem. So we have used Gauss divergence theorem. A dot ds equal to div a dv. Now of course we know that a is nothing but ax dy dz, ay dz dx in the next plane, and az in the next plane will be dx dy. Right hand side you have div a. Div a can be written as dax by dx, day by dy plus daz by dz, and dv can be written as dx dy dz. Okay. Now it's given as this. This is your f field, f vector or a vector, depending on the problem. And this is your a vector. A vector is axi plus ayj plus azk. So you have to compare. That means ax with this component, ay is with this component, az is with this component. So we have now ax is nothing but x cube, correct? You just compare. And ay is nothing but y cube, az is nothing but z cube. So instead of ax, you write x cube dyc, x cube dy dz. Okay, instead of ay, you have to write y cube dz dx. Instead of az, you have to write z cube dx dy. Right hand side, let it be like this. Okay, right hand side. Right hand side, your ax is nothing but x cube, ay is replaced by y cube, and az is replaced by z cube. So now just differentiate with respect to the coordinates. So you have x cube. When you are going to differentiate with respect to x, will give you 3x squared, 3y squared, 3z squared. You pull 3 out. You pull 3 out, that will give you x square plus y square plus z squared. Given that x square plus y square plus z squared is nothing but a squared. So instead of this, you can write a squared. Again, a squared is constant, you can pull it out. So 3a squared dx dy dz. Over volume, it is given as over volume. It is given as where S is the surface area of the sphere. It is given as a sphere. So volume of the sphere is nothing but 4 by 3 pi r cube, which you have learnt in the smaller classes, correct? 4 by 3 pi r cube. Here a is a radius. Okay, so radius is nothing but your a cube. Radius is nothing but your a. So 4 by 3 pi r cube. So 4 by 3 pi a cube. So 4 by 3 pi a cube. So 3 will cancel, and you have 4 pi a to the power 5. So that's the answer for this question. Okay, we are going to answer for evaluation of this vector field, which is nothing but 4 pi a to the power 5. Any doubt on this simple problem? So now find the flux of the vector field f, which is given as zi plus yj plus xk. Okay, first we will come using divergence theorem. Okay, Gauss divergence theorem, and of course right hand side is nothing but triple integral volume del dot a div f dv. We know already. So we will calculate first div f. Div f is nothing but del dot f. Okay, del dot f. Del dot f is nothing but d by dx your z plus d by dy y plus d by dz x. What is the answer for this? What is the answer? 0. Very good. Answer is 1. Here it is 0. Here see with respect to y. So answer is 1. 0 plus 1 plus 0. Answer is 1. Is it okay? So we have calculated now right hand side of the divergence theorem. Is it okay? Divergence theorem. Now the unit sphere S is the boundary of the unit ball. B is given by x square plus y square plus z square less than 1. So we have a sphere. Everything happens only inside the sphere. So that is less than 1. So the divergence theorem gives the flux as this is your divergence theorem. F dot ds equal to div f df. Already we have found out div f, which is nothing but 1. So which is 1 dv. Correct? 1 dv. And of course we know that x square plus y square plus z square as given in the problem is 1. So we have now instead of dv you can write 4 pi 3 pi r cube, r equals 1. So 4 pi 3 pi 1 cube, which is nothing but 4 pi 3. So that's the answer. Simple answer. This problem is very important problem. Verify Gauss divergence theorem for f equals 4xzi minus y square j plus yzk over the cube bounded by. So earlier we were solving for the volume of the sphere. Okay, can you remember? And this is for the cube. So we have a cube bounded by x equals 0 to x equal to 1. The side of the cube ball is x equal to 0 to 1. So 1 1 1. Is it okay? 1 1 1. X equal to 1. Similarly for the other one, y equals 0 to y equal to 1 and z equal to 0 to z equal to 1. Okay, for the cube we have x y z. Okay, x y z and x goes from 0 to 1, y goes from 0 to 1. Similarly z also goes from 0 to 1. So this is a cube, perfect cube. And we are going to evaluate, we are going to verify. We are going to verify means we are going to find out the answer for the right hand side and the left hand side. It should be equal. So this is the idea. Gauss divergence theorem is nothing but this. So first we will calculate, we will go for del dot f. It's easy to calculate. Del dot f. Del is given by this expression and f is given by the problem as shown in the problem. So your del dot f is given by this simple one. So we know already del dot f is nothing but d by dx 4xz plus d by dy minus y square plus d by dz yz. Okay. So now I have written the same thing. You have to differentiate with respect to x will give you 4z, respect to y that will give you minus 2y, and this becomes plus y. Okay. So your del dot f is nothing but 4z minus 2y plus y is nothing but minus y. So 4z minus y. So now right hand side which is equal to del dot f dv. We have already found out del dot f. So which is nothing but 4z minus y. Your dv is nothing but dx dy dz, and of course your limits will be 0 to 1 for x, 0 to 1 for y, 0 to 1 for z. It's a very simple one. Okay. Now we are going to solve triple integral. So 4z minus y. First we will go for x. The answer will be x with the limit 0 to 1. 0 to 1. You substitute now, instead of x substitute 1. The answer is the same thing. 4z minus y dy dz. Now we will integrate with respect to y now. So that will become 4z. You are going to integrate with respect to y now. So 4z y minus this becomes y squared by 2. Is it okay? You are going to integrate with respect to y now. So this becomes 4z y minus y squared by 2. So now 0 to 1. So you have to substitute wherever you find y, you have to substitute the upper limit minus lower limit. So substituting the upper limit will give you 4z. So this is 1 by 2. So 4z minus 1 by 2. Now only one integral is left out. So now integrating with respect to z, that will give you 4z squared by 2 minus 1 by 2 z. Okay, minus 1 by 2 z. Now substitute for z. So that will give you 4 by 2 minus 1 by 2. Correct? So just take the LCM, that will give you 4 minus 1 by 2. Answer is 3 by 2. So we have found out the answer for the right hand side. So this is for the right hand side. See, this is for the right hand side. We have found out the answer for the right hand side. Now we have to go for the left hand side and we should get the same answer. Only then we can verify Gauss divergence theorem. Is it okay? See, we have found out the answer for the right hand side, which is nothing but 3 by 2. Now we will have to go for the left hand side. But left hand side is nothing but f dot n ds. Okay, this is flux. So for that we need to go for the now left hand side. Okay, we need to go for this diagram. And of course flux which is coming out. Okay, so we know it's in the problem it is given as a cube. Boundary for the cube is 0 to 1 in all the three directions. So we have x direction, y direction and z direction, and this is 0 for x direction, so this must be 1, correct? And this is 0 for y and this must be 1, and this is 0 for z and this must be 1. It is bounded by. Is it okay? Diagram is okay. Now what if you just consider this plane? You consider this plane. This is xy plane. Is it okay? Simple. You just consider. Okay. Xy plane. There is no z here. Z component. There is no z component. So z equal to 0. Is it okay? Now you consider this plane. This is xy. This is xz plane. See? And there is no y component here. So y equal to 0. You consider this plane now. We'll consider that side. Okay. Consider this plane. So we have yz plane. There is no x component. So x equal to 0. So first you have to understand this. Is it okay? Now second point. Suppose this is as I said x equal to 0, correct? And this must be x equal to 1. And here x equal to y equal to 0 and this must be y equal to 1. So that's why y equal to 0 I have written here, and this side we have y equal to 1. Okay, first point. The second one is similarly z equal to 0 and here it is z equal to 1. And second very important point is, if you are going to consider this is your I outside vector, okay, outside vector is positive, then we will have to consider 0 as a negative vector. I repeat, see y equal to 1, you have j vector, okay, j vector. For x we have I vector, for y we have j vector, for z you will have k vector. Suppose we are going to consider outward, then if for y equal to 1, so j will be positive. What about y equal to 0 then? It will be minus j. Minus j. If you have to consider this one, so we have I equals positive value, I equals 1. Whereas for this one I will be negative value, so minus I. So this will be minus I, this will be plus I, this is minus j, this must be plus j, this is minus k, that will be plus k. So you have to remember some points like this. Okay. We are going to consider all the 6 faces. In the cube we have 6 faces. So this is your S3 phase, this is your S6 phase, and we have this is S1, S2, S3, S4, S5, S6 phases. In all the phases we are going to compute flux, okay, outward flux. And this is for the first one, this is for the second one, dot for the sixth one, up to 6 we are going to count. For that we need to have a table like this. Given that this is given, so vector field F is given, okay, you should remember vector field F is given. What is the formula on left hand side? Left hand side formula is F dot n ds. Can you F dot n ds? This is the formula, correct? Right hand side we have calculated already. Don't bother about now right hand side. Left hand side is F dot n ds. Now F dot n ds, F dot n ds. Okay, F dot n ds. F dot n ds for the first surface, F dot n ds for the second surface, f dot n ds for the sixth surface. We are going to add all those things, get left hand side. That's the idea. Okay, first we will go for the first surface, S1. S1 is the first surface where x equal to 1. So ABGF, ABGF. So this is facing you, okay, facing you. ABGF. So this is your S1 surface towards you, okay, S1 surface. So we have S1 which is equal to ABGF, x equal to 1. As I said just now, if it is coming outside, your n vector will be your I vector, positive I vector. So you have f dot n. F is given by this. Okay, f dot n. N is nothing but your I vector. So f dot I. Is it okay? Your n vector is nothing but I. F dot I. F dot I is nothing but 4xz. This is 0 and this is 0. Is it okay? I repeat. See here, we have to calculate f dot n vector. Your n vector is nothing but I vector. So f dot I vector. For the first one, f dot I vector. F dot I vector is nothing but 4xz. This becomes 0. This will become 0. So you have 4xz. Now 4xz, x equal to 1. You substitute x equal to 1 here. So you have 4z. So 4xz equal to 4z. Is it okay? So we have found out now f dot n. What are the plane in this plane? See here, in this plane, this is nothing but xy plane. So we have xy plane. So we have dy dz. See, we have dy dz. Where x equal to 1, this side. So we have dy dz. So for x equal to 1 and x equal to 0, we have dy dz plane. Okay, there will be no dx, only dy dz plane. What about for the next one? X equal to 0, S2, as I said, this will go inside. So minus I. See, minus I. The same thing will be there. So here minus I means f dot minus I. So minus f dot I. So that will give you 4xz, minus 4xz. What about for the x value? X value is 0. So answer is 0. So your f dot n equal to 0. F dot n equal to 0. Is it okay? Now we will go for the third one, S3. S3 equals y equal to 1. Y equal to 1. This side. We have this side. So as I said, y equal to 1 means we have j vector. So your f dot j vector. F dot j vector is 0 and this becomes minus y squared. Again plus 0. Is it okay? So now we have minus y squared. So minus y squared. Instead of y, you have to substitute 1. So minus 1 squared, which is equal to minus 1. So your f dot n is nothing but minus 1. Your ds is nothing but dx dz. There will be no dy. Because this is y component. So there will be no y dy. So dx dz. Is it okay? Now for the S4, y equal to 0. So answer is 0. Simple one. Similarly for S6, minus k equal to 0. So you will have 0. And here for S5, we have z equal to 1. So this becomes f dot k vector. F dot k vector equal to 0 plus 0 and this becomes yz. So yz, instead of z you will have to substitute 1. So answer is y. So we have y dx dy. So we know already this. So we are going to substitute it. So we have to substitute. And this is for the first area. F dot n ds, first area. This is for the first one. So we have f dot n ds. F dot n ds. What is f dot n ds? 4z dy dz. So 4z dy dz. And what are the limits? 0 to 1. For y also, for z also 0 to 1. Okay. So now we have 4z. Instead of dy, we will have to integrate with respect to y. That will give you y. Substitute the upper limit. So that will give you 4z dz. Again, when you are going to integrate with respect to z, will give you z squared by 2. So 4z squared by 2. Substitute for z, that will give you 4 by 2. Answer is 2. So we have found out now for the first integral, S1. See, for the first one. And what are these two? S2. S2 is 0. And your S4 also 0. And your S6 also 0. Correct? So S2 0, S4 0, S6 also 0. See, S2 is 0, S4 is 0, S6 also 0. What are the remaining one? S3. S3 is nothing but this. So we have minus 1 dx dz, minus 1 dx dz. Minus you pull it out. When you are going to integrate with respect to dx, that will give you x. Apply the limit. Again this becomes 1. So we have minus dz. Integrate. So that will give you again z. Apply the limit. That will give you minus 1. So we have found out the next integral. The next one, S5. S5 is this one. S5 is this one. Okay, S5 is this. So y is that. So that becomes y. So y dx dy. Y dx dy. So that will give you y. Instead of dx, after integrating, that will give you x. The limits is 0 to 1. Substitute the limit. That will give you y dy. Again, when you are going to integrate, the answer will be y squared by 2. Substitute the limits. That will give you 1 by 2. So very simple. So we have found out now all 6 integrals for the left hand side. All 6 integrals for the left hand side. So this must be 2, 0, minus 1, 1 by 2, 0. So answer will be 2 minus 1 plus 1 by 2. Correct? 2 minus 1 is nothing but 1. 1 plus 1 by 2 is nothing but 1 and a half, 3 by 2. So answer is 3 by 2. So 3 by 2 is exactly equivalent to right hand side C, which we have got. See? Okay. So thus Gauss divergence theorem is verified. Okay, very simple problem. We are going to solve similar problem for different f. Okay. So verify Gauss divergence theorem for this. F equals 3xzi plus y square j minus 3yzk. The same limits are given. The cube bounded by x equal to 0 to x equal to 1, y equal to 0 to y equal to 1, z equal to 0 to z equal to 1. So we know Gauss divergence theorem is given by this. As usual, first we will go for the right hand side. So del dot f dv, you have del is given by this, and f is nothing but this. We have f is nothing but this. So f equals f is given by this. So your del dot f is given by d by dx 3xz plus d by dy y squared minus d by dz 3yz. So I have written the same thing. Now I am going to differentiate. When I am going to differentiate with respect to s, will be give me 3z, and this one will give me 2y, correct? And this one will give me minus 3y. So plus 2y minus 3y is nothing but minus y. So 3z minus y. And right hand side is nothing but del dot f dv. So del dot f dv is nothing but 3z minus y, and instead of dv you can write dx dy dz 0 to 1, 0 to 1 and 0 to 1. Okay. Now first we will go for x integration. So answer is x. Apply the limit. So that will give you 3z minus y dy dz. Okay. Now the next integral is y. So this becomes 3z y minus y squared by 2. Substitute for y for 1. So that will give you 3z minus 1 by 2. You have to integrate with respect to z. That will give you 3z squared by 2 minus z by 2. Substitute for the limits. That will give you 3 by 2 minus 1 by 2. Answer is 2 by 2, which is equal to 1. So the answer for the Gauss divergence theorem for the right hand side is 1. So now we will go for the left hand side. As usual, left hand side is nothing but flux. We have already explained this diagram very well, and we are going to have f dot ds. Total f dot is nothing but for the first side, and this is for the second side. The flux usually will come out only through the surface area. So that's why written as S1, S2, S3. Suppose if it goes like this, this is minus flux. Okay, inward flux. This is outward flux. Is it okay? For x equal to 0, this is inward flux minus I. X equal to 1, this is outward flux. So for x equal to 1, this will be plus I. Okay. So similarly, you have f dot n. We are going to calculate f dot n. So here for S1 this one. So we have now x equal to 1, and you have positive I. F dot I will give you 3xz. You have to substitute for x as 1, so that will give you 3z. So f dot n is nothing but 3z, and your ds is nothing but dy dz. And S2 become 0, S4 will become 0, S6 also will be 0. And you have S3 as usual, y equal to 1, and this becomes positive outward flux J. And you have F dot J is nothing but y squared, which is equal to 1 squared. You will have to substitute for y equal to 1. So that will become y squared equal to 1 squared. So answer is 1 dx dz. And for k, F dot k is nothing but minus c minus z. So minus 3y z, which is equal to minus 3y dx dy. Okay. And we'll have to sum over all the 6 sides, the flux of the all 6 sides, S1, S2, S3 up to S6. Okay. So we have F dot n ds is nothing but 3z dy dz. So 3z dy dz. So 3z with respect to y, you integrate, that will give you y. Substitute for y, that will give you 3z. Again you have to integrate with respect to z, that will give you 3z squared by 2. Substitute for 1, that will give you 3 by 2. Correct? 1 square, 1 by 2, so 3 by 2. So answer is 3 by 2. For S2, S4, S6 all will be 0. So all become 0. And for S3 we have F dot n ds is nothing but we have 1. So 1 dx dy dz. So integrating with respect to x will give you x dx. So we have substituting the limits, that will give you this 1 dz. Again we are going to integrate with respect to z, that will give you z with the limits 0 and 1, so that will give you 1. And for S5 we have S5 is nothing but minus 3y. So minus 3y dx dy. So first you will have to integrate with respect to dx, that will give you y x 1 0, substitute the limit, that will give you 1. So 3y minus 3y, y squared by 2, substitute the limit, that will give you 3 by 2. Okay. Now you will have to add this 3 by 2 plus 0 plus 1 minus 3 by 2. So 3 by 2 plus 1 minus 3 by 2. 3 by 2 and 3 by 2 will get cancelled. So answer is 1. Already we have found out the left hand side, which is nothing but 1. So right hand side also is 1. So left hand side equal to right hand side. Hence Gauss divergence theorem is verified. Okay. So thank you students. We will see in the next class.